Welcome back to an example of 3.4, and we are going to find all the real zeros to this polynomial. All right, first of all, this is a 5th degree polynomial because its highest power is 5. So it is possible for us to have, or from the pieces that we learned before, all that information I dumped on you, is it could have 5 zeros. Does not say that all of them will be real, but in this section they're not going to have you find the real zeros if they're not all real. They're going to save those for 3.5. I am only going to do one example here, so I would suggest you also look at my 3.5 examples, because a lot of the techniques I use here we will use there as well. So, okay, so this is what we've learned. Or this is what all that information tells us. First of all, if we're going to find real zeros, now real does not mean nice. However, most textbooks and most problems that we're going to be doing will be nice. Real just means real, which means we could have the square root of 2, the square root of 7, the square root of 13, all of those real ugly pieces show up here as well. So I want you to think of the quadratic, so an x squared. The not nice ones come from that quadratic formula. And you'll notice sometimes they will have that squared piece in them. So you gotta have to be a little bit careful. We could have ugly things. But in this section, they don't do that to us unless it gets down to that quadratic. And then you can use the quadratic formula to finish. But we have at most 5 zeros because it's a 5th degree. We aren't going to have 6, we'll have 5. So we also had that one theorem in this section that says that all of our rational zeros, so all of the real nice ones, will look like that P over Q thing, where P is a factor of the constant term and Q is a factor of the leading coefficient. So what I'm going to do is first of all list all my possible pieces. So all possible. So I'm going to take 9 and I'm going to list all of its factors. So 9 has, well, 1, and they could be plus or minus. We also have 9, so plus or minus 9 and plus or minus 3. We like it when we have just a limited number. So when we have like 48, that's a really long list. Our possibilities for Q are plus or minus 1 and plus or minus 2. So all the possible rational zeros that we could have are these ratios. So we could have the 1 over 1, so plus or minus 1. We could have 1 over 2, so plus or minus 1/2. We could have 9 over 1, so plus or minus 9. We could have 9 over 2. We could have 3 over 1, which is just 3. And we could have 3 over 2. So there's all of our possible real rational zeros. Not all the possible real ones, but all the possible rationals. Since we had integer coefficients, rational zeros will look like this. So these are the only possibilities for rational numbers. So now we're going to look at Descartes' rule of signs and see if we can get rid of some of them or a little bit more information. Rule of signs. Okay, what we are going to do is we're going to look at the original equation and we're going to look to see the sign changes. So our sign changes here were positive, positive, we became negative. That's one sign change. Then we became positive. So we had 2 sign changes. Okay. In the original equation. So the original one, we have 2 sign changes, which means by Descartes' rule of signs that we have either 2, so the same number, or less than that by an even integer. So go down from here by 2 every time. So 2 or 0, positive zeros. Okay, so we're either going to have 2 or we're going to have 0, positive zeros. We're also going to look at the negative. So I'm going to put a negative x in here. If I put a negative x in here, this becomes negative 2x to the 5th plus 5x to the 4th, because negative x to the even power is even. This is going to change the sign. This one's going to stay the same. This one changes the sign, and that guy stays the same. So looking at our sign changes of p of our negative x. P of negative x, here we're negative, then positive, then negative, and then positive. So we have 3 sign changes, which means we have either 3 or 1 negative zeros. Okay. Now remembering that we have to have 5 zeros, we know that something's going to happen here. We could have some non-real zeros going on too, but my guess is the only way to get on in this section, since we're in 3-4 and not in 3-5, we're going to have 3 negatives and 2 positives, simply because I need 5 total, and this does take into account the multiplicity, so something occurring more than once. We aren't going to get 3 and 0. Or 0 and 1, because that's only going to give us 1. We have to get this 2 and 3. So we get our 5 zeros. All right, so what we're going to do is we just got to start checking. And that's the bad part, is we just are going to have to see and pick something and say, okay, let's see if it works, and find a 0 or not. So, I don't know. I also kind of look at, remembering that it's a 0, if I put it in here, it has to make 0. So again, this is where we got to kind of get lucky. And I'm just going to check the number, I don't know. And the reason I'm doing this number is because I know it's going to work, but maybe I'll just try one that's not. So let's just try 3. So we're just going to see if 3 is a 0. I don't know. Try it or not. And I'm going to substitute it, so I'm not going to put it in. Some people, they do this 2 different ways. You can substitute 3 in here and see if you get 0. So take 3 to the 5th times 2, 3 to the 4th times 5, and all of that, and see if it works. I usually check by doing synthetic division. So I put my 2, my 5, my negative 8, negative 14, 6 and 9, 5, 4, 3, 2, 1, 0, making sure I have all of them, and I check this way. And it usually doesn't take me too long to realize if it's going to work or not work. So I'll bring my 2 down. 2 times 3 is 6, and I add 33, and I add, carefully add, use my calculator and cheat to add 75, oh boy, 61, 183, whew, that's going to be, obviously it's not going to work, but I'm going to do this for a reason. I'll show you my other reason here. What is that, 189? 189 times 3 is 567. So this is 576. Okay. Notice, first of all, it isn't a 0 because I didn't get a 0 here, but I also wanted to use this 3 as an illustration. You'll notice that all of these were positive, which means by that upper and lower bound thing, 3 is an upper bound. 3 is an upper bound. which means that I don't have any real zeros that are larger than the number 3. So in other words, this just threw out a couple of my other examples. I know that 3 is not going to work, but I also know 9 isn't going to work, and I also know that 9 over 2 is not going to work. So I can check something a little bit smaller. And I might even want to have tried a negative to begin with because there's more choices for my negatives to possibly work. So I'm just going to just try another one. I don't know. And this is where we hope we get lucky comes into play. So 2, 5, -8, -14. And I'm just going to pick a nice, easy number this time. I'm going to try 1. I always try my nice small ones first and pray that they work. So bring my 2 down. That gives me a 2. This gives me 7. This gives me 7. -1. Did I do that right? So -1. -15. -15. -9. There. Okay. The nice thing about what happens when you find a 0 is it also decreased your powers down. So this is what now? 2x to the 4th plus 7x cubed minus x squared minus 15x minus 9. So I have just written, there's my original, this guy right, whoops, no, that's not my original. This is my original. This guy can now be written as this one times x minus 1. I have factored out that x minus 1. And now I'm down to a 4th degree polynomial. So I now know that my other zeros are going to come from this. The unfortunate thing that has happened is I didn't decrease my possibilities. Those possibilities that we had, since I'm still with the 2 and the 9, the possibilities haven't changed. But I do know that the 9 and the 9/2 aren't going to work because of that upper bound thing. I also can check to see Descartes' rule of signs. Notice my sign change is 1 here, which means I also knew that if we found one real positive one, this isn't going to be the case. We are going to find another one. So there is another positive 0 out there. I do know that it's going to be either another 1, because of multiplicity, or I also know that if there's 2 positives, we could look at that negative. So I could do that and find out that we're going to have those 3 still negative zeros. I'm going to go after some of those negatives. I'm just going to attempt. So I'm going to try that -1. But instead of going into the long one, I know it's got to come from here. So I'm going to just work with those numbers. So that's 7, 2, 7, -1, -15, and -9. And see what happens. All right, so we bring down the 2 times -1. We add. And this is where you have to be careful with your signs. -5, add. That gives me -9, 9, and add. And now I'm down to this guy. But again, my 9 and my 2 didn't change. But I do know that I now have an x plus 1 from this guy and the x minus 1 from before, and then this guy on top of it. Okay, I do want to start pointing some things out. Notice our powers are decreasing. Now we have 4 terms. So I would look at this thing pretty hard to see if I could factor it by grouping. Because 4 terms, little bells should go off. Oops, I forgot my squared. Little bells should be going off. Factor by grouping, factor by grouping, factor by grouping. I'm going to look at this a little bit with that 5 in there. Oh, unless I could pull the 3 coming out to make this a 2, that's not going to give me a 5. So it's not going to work. So I got to go another time. I'm just going to continue this one. I do know that -1 works. And the only reason I know this is because I've done this problem before. You guys wouldn't know, so you'd just be like trying things. You just keep trying values and praying that you get one that works. I always like to start with nice 1s and 2s and negatives. I leave the fractions to pray they work later. So I'm going to bring that 2 down, adding, that's going to give me a negative 9. Okay, so I'm now down to 2x squared plus 3x minus 9. So I now know I have x plus 1 twice, and that x minus 1. And I also know that now I am down to a quadratic. So I can find the zeros by factoring, if at all possible. So I'm going to factor this if I can. So I'm going to multiply those two guys together, so negative 18. So I'm thinking two numbers that multiply together to give me a negative 18, that add together to give me a positive 3. Multiply together to give me a negative 18, add together to give me a positive 3. How about 6 and 3? Out of these two, I can pull out a 2x. That would give me x plus 3. Out of these, I will pull out a negative 3, which gives me 2x minus 3 and x plus 3. So my other zeros are going to come from these guys. So negative 3 is a 0. And if I had checked it, it would have worked. This one would have been a little harder to find because, first of all, we don't like to work with fractions. So it would not have been one that we checked. But there's our other positive 0, that 3x, that 3 halves. So our zeros are 3 halves, negative 3, negative 1, and if you want to write it down twice, negative 1, and positive 1. So there are our 5 real zeros. We could have factored this into x minus 3 halves, x plus 3, x plus 1 squared, I'll write that, and x minus 1. Notice we don't have our leading coefficient. We could pull that out. And if I multiply that into this first one, it would turn into that 2x minus 3 that we had here. So if you want to write them as linear factors as the x minus c's, you're going to have the fraction in there, and that leading coefficient pulled out. Or you can multiply that leading coefficient in, depending on how they want it written. So here's an example of finding our 5 zeros. These problems take time and a lot of luck. So good luck.